We have 4 different types of mole conversions that we use: molar mass, balanced chemical reactions, Avogadro's number, and we can also find mole conversions in chemical formulas. For this video, I do some problems that require that you already have watched the molar mass calculation video and Avogadro's number. So if you haven't done those yet, take a moment and take care of that, as well as the introduction to moles and familiarity with what a compound formula is first. What does the formula tell us? Well, let's consider copper to nitrite. In terms of moles, we know that if we have 1 mole of this substance, NO2, actually, let's back up for a minute. Rather than starting with moles, let's say we have 1, I want to say formula unit. Oops, I'm erasing. 1 formula unit, which, remember, is just the same type of phrase that we would use to say molecule. So we're really talking about a molecule, but because this was an ionic compound, we use the term formula unit. So you can kind of think of this as a molecule. So that gives you a frame of reference for how small we're talking. And we know from our discussion of formulas that in 1 CuNO2, we would have 1 atom of copper, for instance, or 2 atoms of nitrogen, or 4 atoms of oxygen. The power, and really the sort of amazing thing about moles, is that if I change my frame of reference from 1 of these to 6.022 times 10 to the 23rd of these, then what happens to my number of copper atoms? Well, it's still a 1-to-1 ratio, so I have 6.022 times 10 to the 23rd atoms of copper. Now, the mole allows us to shortcut having to write these really large numbers, because really, this is 1 mole of copper to nitrite, which means that in 1 mole of copper to nitrite, I have 1 mole of copper. I also have, using the same ratios that I did above, 2 moles of nitrogen, or 4 moles of oxygen. So all I'm doing here is taking my formula and noting I've got 1 copper and 2 nitrogens and 4 oxygens. Each of these that I've just drawn down here, this relationship, this set of relationships, each of these is a conversion. So, when should you use this type of conversion? We've talked about the fact there's these 4 different types of mole conversions. Molar mass, Avogadro's number, using the formulas, and using balanced chemical reactions. And that can get a little overwhelming because you start to wonder, well, when do I use what? So let's look at some example problems that we're not actually going to do the calculations for. We're just going to assess the problem and whether we would need to use this type of conversion. Now, this conversion that we're talking about, let's go back here for a moment, is where we would see an element, some kind of element, and its relationship to a compound that it's a part of. So we're looking for some kind of problem that relates an element to the compound that it's a part of. So when we read this first question, how many grams of sodium, okay, so I'm looking at an element there, are present in a 32.0 gram sample of sodium cyanide? What I notice here is I'm asked to find something about the element sodium, and I'm given information about sodium cyanide, which is the compound. So we've got Na here, and sodium cyanide has a formula of NaCN. So the problem's letting me know, hey, at some point I'm going to need the relationship between sodium and sodium cyanide. And that comes from my formula right over here. We can see that in 1 mole of NaCN, I just look at the formula and see I only have 1 mole of sodium. So at some point in solving this problem, I'll need to use that relationship. Let's check out another one. How many formula units of potassium sulfate are present in a sample which contains 5,500 moles of potassium. Again, I notice that I have a compound here, and I have an element that is part of the compound also in the problem. And so that tells me if I'm starting here with my element, here's the element, and I'm eventually going to need to get to the compound that the element is a part of, then I'm going to need to know the formula of potassium sulfate, which is this, and to recognize that if I have one K2SO4, I have two Ks. So I have 2 moles of potassium. So this again is a type of problem where I need that element to compound formula relationship to solve the problem. In our third example, how many grams of sodium chloride are react with 5.00 grams of silver nitrate? What I noticed in this problem is that I want to know the grams of sodium chloride, which is one type of compound, and it tells me R reacted, which is suggesting I'm going to have a reaction somewhere, with 5 grams of silver nitrate. Now, what I notice here is we have NaCl, and we want to know how many grams of that. And I'm given 5.00 grams of silver nitrate. Nowhere in this problem am I referencing a particular element. So I don't have sodium chloride and then I'm asked about sodium or chlorine. I have sodium chloride, I'm asked about a completely different compound. So for this last problem, we know we would not be using the element to compound formula, molar ratio. So we wouldn't use it on the last one. So here's one that we'll actually do. How many atoms of chloride are present in a 10.0 gram sample of calcium chloride? And we're noticing here's chloride, here's calcium chloride, this is the element, this is the compound. Somewhere along the way I'm going to need the relationship between the two of those, and that will come from the compound formula. Calcium chloride is CaCl2. So in 1 mole of CaCl2, I have 2 moles of chloride, Cl-. So I'm going to start with the number that I'm given here, which is this 10 gram sample of calcium chloride. 10.0 grams of calcium chloride. If we have grams, and we know that eventually we're going to need this relationship up here, which is in moles, it means that I'm going to need to use my molar mass, which I can calculate from the periodic table. And when I do that, I see that my calcium chloride is 110.98 grams per 1 mole of CaCl2. That moves me into moles of calcium chloride, and I know from my element to compound formula or relationship up there that 1 mole of CaCl2 is 2 moles of Cl-. Finally, I'm in chloride, but now I want to see how many atoms. So I have a last step, which is to change from moles of chloride minus to atoms. And to do that, we know we have to use Avogadro's number, because that's the only conversion that we have at our disposal that involves atoms. Well, technically, this should be ions of chloride. You get the general idea. Let's make this ions. Make this ions. Okay, so then we pop these into our calculator. We have 10 divided by 110.98 times 2 times 6.022 times 10 to the 23rd. I get 1.085. And I notice that I have 3 significant figures in my measurement, so this needs to become 1.09 times 10 to the 23rd ions of chloride. One more example. You have magnesium nitrate. It contains 34.0 moles of nitrate. How many grams of magnesium nitrate are present in the sample? Well, again, we notice this time it's not telling me about a particular element, but it is telling me about a polyatomic ion that is present in this compound right here. Magnesium nitrate has a formula of MgNO32. So we know that 1 mole of magnesium nitrate contains 2 moles of nitrate. And I'm picking up on this 2 because there was a 2 in the formula. I start with 34.0 moles of nitrate, -1. And now I want to think about where I want to go. I want to go to grams of magnesium nitrate. So I need to get out of nitrate and into magnesium nitrate. I know that there are 2 moles of nitrate to 1 mole of magnesium nitrate. And finally, I'll use the molar mass of magnesium nitrate to get to grams. And that molar mass is 148.33 grams. Everybody goes into the calculator. 34 divided by 2 times 148.33. I get 2521. I only have 3 sig figs, so this becomes 2520 grams.